So we finished yesterday by drawing a diagram of where you might find the electron. If I go 0.529 angstroms away, the probability of finding an electron is 59%. If I'm closer than 0.529 angstroms, then my probability is less than 59%. If I'm farther than 0.529 angstroms away, my probability begins to decrease and it's less than 59%. There are only two places where there's no probability or zero probability of finding the electron, and that is at the nucleus and out there at infinity. Now this graph took into account 4 quantum numbers, and those 4 quantum numbers were n equal to 1, L equal to 0, M sub L equal to 0. So in other words, this was the first fundamental wave with one amplitude, no angular momentum, no magnetic field, and then our 4th quantum number has to do with spin. The electron can be spinning clockwise or it can be spinning counterclockwise. So I arbitrarily picked plus 1/2. So this diagram explains, or these 4 variables get plugged into that diagram. So for an electron that has those 4 values, our probability graph will look like that. And I want to stress that point again. What we have graphed is a probability graph. This is not the path the electron takes. The electron is not going like that. This is a graph of where you might find the electron when it has these 4 values. So if n is 1, L is 0, M sub L is 0, and I have a plus 1/2 spin, then the probability of finding the electron 0.529 angstroms away is 59%. Now, here's where things begin to get kind of weird. Suppose I want to graph the first 3 quantum numbers the same, but I want to now do it for an electron that has got the opposite spin. Well, as it turns out, the graph looks exactly the same. So for an electron that's spinning clockwise, the greatest probability of finding it is 0.529 angstroms away. But for an electron that's spinning counterclockwise, so here's one spinning clockwise, here's an electron spinning counterclockwise, the probability of finding a different electron spinning counterclockwise is also 0.529 angstroms away. So in other words, if I had 2 electrons, each with a wave value of 1, each with 0 angular momentum, each with 0 magnetic field, but the difference is one electron is spinning this way and the other electron is spinning the other way, the probability, the best place to look for both of them is 0.529 angstroms away. So in other words, what you're saying is the greatest likelihood for 2 different electrons is to be in the same place. The greatest probability of finding 2 electrons, as long as they're spinning in opposite directions, are in the same place. So in other words, it's possible for 2 electrons to occupy the same space at the same time. You obviously cannot do that at the macroscopic level. It would be like saying 2 students can occupy the same chair as long as they're rotating in different directions. So once again, this graph is just a probability graph. It tells me the most likely place to find an electron. And we have a special name for that. We call it an orbital? An orbital is a probability graph. It does not tell you the path of the electron. Planets orbit. Planets go in a definite path. Moons orbit around planets in a definite path. Orbitals are probability graphs. So do not confuse orbits and orbitals.